want to try to find the electric field due to an infinite sheet of charge. So imagine this sheet exists in the YZ plane and it extends to infinity in every direction. And we want to find the electric field at any point along the x-axis which is perpendicular to the sheet. So the first thing, as usual, we need to find is what is the direction of the electric field everywhere in space. So let's assume that the electric field has a component perpendicular to the sheet and also parallel to the sheet. And we're going to show by contradiction that it cannot have a component parallel to the sheet. So the argument is the same as usual. We're going to rotate the whole sheet and the electric field vector, everything we rotate it by 180 degrees about the x-axis. To do that, this is what you get. The sheet stays exactly the same as it was, but the electric field vector gets rotated by 180 degrees. Now this can't be the case because you can't have the same charge distribution producing a different electric field vector. So the only way for this to happen is for the electric field to point radially out, perpendicular to the sheet. So this is the only way that the electric field can point in this problem. So another thing we can think of, if you keep the same distance away from the sheet and you move from point 1 to point 2, keeping the distance the same, you expect that the value, the magnitude of the electric field to be the same. And the reason is because when you move from point 1 to point 2, everything looks exactly the same. The sheet is infinite, so you don't get closer or farther away from the ends of the sheet because there's no end. It's completely infinite. So this is the picture we have. You have the electric field on this side is pointing this way, and on this side it's pointing this way, and assuming in this problem that the sheet is positively charged, for instance. So what shape Gaussian surface would you choose, and where would you put it? Remember, the choice of the Gaussian surface is based on trying to get rid of this dot product. Think about it a little bit and then continue. So let's take a rectangular volume like this, and it has it's equidistant on either side. This side is the same distance as this side, and this is the part on the other side of the sheet. That's why you can't see it clearly. It's transparent. Imagine the sheet is transparent so you can see the part that's behind. Now, why do we choose this rectangular volume? Because if you look at the area vector on the top face, it's perpendicular to the electric field because the electric field is perpendicular to the sheet. So the angle is 90 degrees, so you get zero flux through the top face. The same thing you can show for the side, this face. All the side faces, the angle between area vector and electric field is always 90 degrees, so you get zero flux. For the front face, the angle is exactly zero, so you get rid of the dot product. Now for the back face, we know that the electric field, if the charge is positive, the electric field will be pointing radially outwards. Now what direction will the area vector be at that location? Since the area vector has to point from inside the volume to outside, that means the area vector points exactly in the same direction as the electric field, so the angle is again zero. Of course, since the Gaussian surface is put on equal distance on either side, that means if you find the electric field on this side and you find the magnitude of the electric field on this side, they would be the same value. We're going to use this during the derivation. So the integration over the closed surface of the rectangular volume consists of three parts. The sides meaning the top and this side and the bottom and the far side. And then there's the front, and then there's the back. For the sides, we said that all the sides, whether it's the top or the bottom or the front face or the back face, they all give you zero flux because the angle between the area and electric field is zero. For the front and back face, that's the only part that will contribute to the flux. So for the front face, the angle between electric field and area is zero, so integration of E dot dA becomes integration of E dA cosine theta, and since theta is 0, cosine theta is 1, so you get integration of E dA. Now remember we said that if you move on the surface of this front face to any point, keeping the distance the same, between the point and the sheet, the electric field should be the same value from symmetry. That means that I can take E outside of the integration. So you get E times integration of dA, which is the area. For the back surface, also the angle between the electric field and area vector is 0 degrees. So that means integration of E dot dA becomes integration of E dA cosine theta, and cosine 0 is 1. So you get integration of E dA, and the same argument as before. If you move at any point on this back surface, since the distance is the same from the back surface to the sheet, that means you expect that the electric field should be constant, and you can take it outside of the integration. So you get E times A. So for the front surface, you get E times A. For the back surface, you also get E times A. And this is where a lot of people have confusion. They think that there should be a minus sign here, but as we showed, the angle is 0 degrees between the electric field and area vectors, so you get positive, both positive. So the left-hand side of Gauss's law is 2E times A, and now we want to know what the right-hand side is. What is the charge inside this rectangular volume? If you make this volume a little bit transparent, you can see that the intersection of the rectangular volume with the sheet is a square. The surface here, assume it's like a square, and so the area of this square is exactly the same area as the front face, is exactly the same area as the back face, and so the amount of charge there is simply sigma times A. Sigma is the charge per unit area. You multiply by the area, you get the total charge on this square part. We can substitute sigma times A for the charge inside, and the area is going to cancel with the area, and you get the final equation, which is that the electric field equals to sigma over 2 epsilon naught. Now look at this result, because it's a bit strange. It's telling you that the electric field doesn't depend on distance. It doesn't depend on x in any way. So if you go to this point on the x-axis, or you go to this point on the x-axis, the electric field, the length of the electric field vector is exactly the same. It never becomes smaller. And this only happens for an infinite sheet. Try and think about how you can justify this intuitively. Now, what happens if you have two infinite sheets? Let's say you have a positively infinite sheet here and a negative infinite sheet here, and they have exactly the same charge per unit area, but they're just equal and opposite. We want to find the electric field everywhere, which means on this side, in the middle, and on the left. So on the right side, the electric field vector due to the positive sheet is pointing away from the positive sheet, and it has a value sigma over 2 epsilon naught. The electric field due to the negative sheet is pointing towards it, and it also has sigma over 2 epsilon naught. Why does it have exactly the same value? As we mentioned before, the distance between the point where you calculate the field and the sheet doesn't affect the value of the electric field, because the electric field is a constant. It never changes with distance. So these two vectors, when you add them, you get exactly 0. And on the left side, the same thing happens. This electric field vector is due to the positive sheet of charge. This electric field vector is due to the negative sheet of charge, and they have exactly the same length, even though the distance between here and here is not the same as the distance between here and here, because the electric field doesn't depend on distance for an infinite sheet. And inside, the electric field doubles because the electric field due to the positive sheet points away from it, and the electric field due to the negative sheet points towards it, so they point exactly in the same direction. So the total electric field will be double each one. You get a total electric field of sigma over epsilon naught in the middle, and 0 outside.